Okay, so here's where we were. We were talking about this computation of volume, right? And we did an example of this. Instead of computing a double integral, we can compute volume with a single variable integral of a single variable integral. And we went through the details in that last example. Okay, so here, however, is what I think is the bigger point. Right? So we viewed this as, hey, I'd like to compute volume. How do I go about doing that? Answer, iterated integral. The more important interpretation, though, is this. We had already computed volume with a double integral. We have now computed volume with an iterated integral. Right? The more important suggestion is this. It's not that volume itself is the thing that we're interested in. It's that now we have this suggestion that, hey, if you want to compute a double integral, for whatever reason, then an iterated integral should do it for you. Now, I'm putting some disclaimers in there. I'm saying, suggests, and we should be able to. Because again, this was not intended to be a rigorous argument, and I'm kind of using geometry to bypass what would be some points of rigor that I just don't want to get bogged down in. And furthermore, I want you to have this geometric intuition for why it kind of really should be that double integrals should be computed with iterated integrals. But anyway, so it's not a rigorous argument, so thus the disclaimers. The punchline, though, is that as long as the functions in question are all continuous, this actually is true for all double integrals. So again, the big takeaway is not that we have a new way of computing volume. The big takeaway is that now we have a new way of computing double integrals. Okay. All right. Right. Okay. Now, notice in this example that we did here, we did our first slices perpendicular to the x-axis, right? And I'm going to say perpendicular to the x-axis for this first part of the slicing process, as opposed to parallel to the y-axis, because importantly, what we end up by slicing this way, we end up with an x integral. So just going forward, so you know, I will always talk about what axis are you slicing perpendicular to, because that is the axis of the variable that's the variable for the resulting integral. Does that make sense to everybody, I hope? Okay. All right, so why do we slice first perpendicular to the x-axis? Couldn't we have instead sliced first perpendicular to the y-axis? Yes, we totally could have. There's no particular reason that I did my slicing on the outside, first slicing perpendicular to the x-axis. It was an arbitrary choice. So here's an exercise that I want y'all to do on your own. There's a whole section here in the book called Switching Differentials where I do it the other way. Right? Where here, notice, we're doing our first slicing perpendicular to the y-axis, thus resulting in an outside integral that is a dy integral instead of a dx integral. And then let me just say, et cetera, et cetera. Right? How do you compute the area of this cross-section? By the way, notice area of the cross-section is now area as a function of y, not x. And so all the variables are kind of playing different roles or sort of traded places, if you will. So a bunch of little more details. How do you find the area under this? How do you find the area of this cross-section? What's the area of that curve? That area is an integral as x varies for a fixed constant value of y. Details left for y'all to read through, work out on your own. Now the punchline is that while we developed this formula previously, you can think of a double integral as being a dx integral of a dy integral. You could just as well think of it as a dy integral of a dx integral. Doesn't matter which way you go. Okay. So, said differently, you've got a couple options. If you want to compute a double integral as an iterated integral, you get to choose which way you want to go. Now, the one thing that I do want to call your attention to, this is a sticky little detail. The range of values for x is, of course, the bounds on the x integral, independent of whether that x integral is the inside or the outside. And likewise, the range of values for y, that's the bounds on the y integral, independent of whether it's on the inside or the outside. So said differently, doing a double integral over a rectangle, you're going to have a couple of bounds over here, a couple of differentials over here. When I say switching the differentials, we're talking about this, right? The bounds have to go with the differentials. That's not optional, right? This is what I mean by it's really switching the order of the integral, of the two integrals, I should say. So anyway, make sure do not do this. That doesn't work. That doesn't make any sense at all. Everybody see what I'm talking about? All right. Okay, so I want to do another. I'm going to let y'all read through this example. The only detail of interest in this example is that we start with, on the inside, dx as the integral. So notice x is the variable. So x squared integrates as 1/3 x cubed. Y, for the purposes of that inside integral, y is a constant, so y squared is a constant, and its integral is just xy squared. Okay. All right, everything else is details. Y'all read through it. It's a lot like what we've already done. Okay. The last thing I want to do is go through how this affects examples other than volume. And the short version is that this idea that we discussed here in the context of volume, right? So we computed volume, which we'd already computed a different way. The point is, this is relevant for far more than just a computation of volume. I already made this observation that think of it as a motivation for how we compute double integrals. Right? Anything that you can compute with a double integral, whatever application you have, if you can compute it with a double integral, you can compute that resulting double integral with an iterated integral. Okay. All right. So I'll show you a quick example of this. Here we go. Suppose I want to compute the mass of a sheet of metal. We already wrote it as a double integral. And then we ran into this dead end, right? I was, wide-eyed scared about, oh my gosh, are we going to actually have to compute this mass by computing the Riemann sum that represents this double integral? Yikes, what a nightmare that would be. Thankfully, no, we don't have to. We can compute that double integral as, take your pick, either of these iterated integrals, nested integrals. Doesn't matter which one. Okay. Now, that said, I do want to point out, and I think this is an important observation, students very often then want to say, oh, well then what's the purpose of the double integral in the first place? Why don't I just go straight from the question right to the iterated integral? Why mess around with double integrals if we're just going to rewrite the double integral as an iterated integral? And I think there's a really important answer to this question. And that is, this iterated integral, we've got a motivation for why the iterated integral relates to double integral, right? But I think we have a much hairier problem in front of us if you want to directly relate an iterated integral to a mass. And here's why. What were we told about the mass in the first place? And here, let me just momentarily just do that. What were we told about the mass in the first place? Well, we were told the density. And in this context, this density, this delta, that delta right there. Here, let me do this. This density is mass per unit area. Right? Now, in this double integral, it's extremely believable that if you take mass per unit area and then you multiply by area, you get the amount of mass in that little piece. You're adding up a bunch of little pieces of mass. This makes great sense. This is an easily relatable first step. No problem. But let's look now at this iterated integral and try to make analogous sort of sense out of, the very first thing that we would have to write down in here is this inside integral. What sense does it make, I ask, to take mass per unit area and multiply by width? Right? That's a mismatch. I mean, mass per unit area times width gives you, I don't know what that is. Is that thing, whatever it is that thing an accumulating quantity? This is really confusing. This is not physically natural, right? This is not something that you can, this is not an obvious breakdown. Now, if you really want to, if you want to cram it in there, yes, you can make sense out of mass per unit area times length. You can develop that idea, but it's an awful lot of trouble and it's totally unnecessary, right? Because rather, instead, let's just let the existing development do our work for us. Mass is a double integral. No hairy development required. Double integral is an iterated integral. Theorem. Right? So that's easy, right? But it would be you'd be off in the woods on your own, exploring, hacking a new trail if you try to directly compute mass as an iterated integral. It just doesn't directly make sense. Okay. So, for whatever that's worth, now students sometimes say, well, yeah, okay, well then what's so special? What is so special about volume that makes that one okay and mass not okay? And the answer is that geometry. Right? Volume is special. Geometry is special among applications because we have what I like to call an intermediate concept. So volume is what we're trying to compute. If you want to view volume as something times a width, we have this pre-existing geometric concept of area. That's a thing. We dig that, right? We know what area is. I know that area times width gives me volume. So it's just, this is literally an easier context in which to make an argument about double integrals being computed as nested integrals. And if the question is mass, we just don't have it. Okay. All right. So in this course, let it be known that I do require. Let's see, where is it? Yeah. So you have to write down as step one of your problem. You've got to give me a double integral. And having written down a double integral, then of course you are then subsequently going to rewrite it as an iterated integral, and then off you go. I mean, computing the iterated integral, that's, for sure, that's the whole reason we do iterated integrals. Right? But the double integral here is not an optional step. I want to see it in recognition, doff of the cap, that this is part of the thought process. Okay. Okie dokie. Okay, so moving along. Let's see here. We are going to talk about non-rectangular domains. This is a little bit of a scary concept. If your domain's not a rectangle, nothing that we've written down previously technically applies. If you look back at the definition of an integral that we wrote down the definition of an integral over a rectangle. And it had to be a rectangle because we chopped it up into n pieces that way and n pieces this way, and summation I goes from 1 to n, j goes from 1 to n, that makes out the entire rectangle. What if it's not a rectangle? By the way, life is chock full of two-dimensional things. Accumulations over regions, two-dimensional regions, that are not rectangles. Right, so this is a big deal, and this is a kind of a hairy matter, and this is something that we're going to sidestep the formalities here. I'm not going to write down formally the definition of an integral over a non-rectangular domain. What I'm going to do is make the case that the intuition is the same. Right? So I appeal to your, intuition about how mass works, for example. That if I have, sitting here in the XY plane, if I had a non-rectangular, let's say a triangle, sheet of metal, right? If I were to chop this up into little pieces some way, right, the total mass would be the sum of the little masses that I sliced it up into. Right? I mean, it's pretty clear. And furthermore, on each little piece, right, if I ask how much mass is there in that little piece, it doesn't matter that it came out of a rectangle. On that little piece, the amount of mass in there is going to be density times area. So look, so the definition, if I were to say double integral over a non-rectangular domain, well, I hope you would have the same sense of what I'm talking about. We're talking about taking this region, chopping it up into a bunch of little pieces. On each little piece, multiplying an integrand times the size, and then adding up over all of those pieces. And exactly the details of how we're going to add that up, we'll get to momentarily. But from the definition, I hope it's reasonable for me to not write down formally what the definition is and just say, well, it's exactly what you think it is. Pretty much. Okay. All right. And the idea of understanding double integrals over non-rectangular domains with nested integrals still works just fine. And I'm going to explain by example how that works. Let's start by thinking about a triangle that has these three vertices. Here it is. Triangle in the XY plane that has those three vertices. And suppose I wanted to know the volume sitting over that triangle and under the graph of where's my function? Yeah, here it is. This function f of xy, looking under the graph, volume under the graph. Right? So here's that surface. And this volume, I hope this looks familiar. It looks just like the previous picture that we drew here, though our loaf of bread didn't rise, right? But so this odd, sad little shaped loaf of bread, even if I cook it in a triangular pan, it is still true that the total volume of bread is the sum of the volumes of the slices of bread, right? That's more a statement about how volume works than it is about rectangular shapes, right? So the total is the sum of the slices. Still continues to be the case. Along those same lines, on each particular slice, right, we're looking at the area of that cross section times a thickness, a width on the x-axis. Yeah? Yes?
Just quickly, so the x in parentheses is it's the x cross section. It makes me think of like function, like a of x.
Yeah, so that's this x right here. So that x in parentheses. So yeah, it's confusing, right? Because x is playing two different roles at different stages in this calculation. Here, when I say let's consider all these slices as x goes from 0 to 1 in this case, x is a variable. Yeah, but then, having written that down, a is a function of x. I mean, you give me an x, there is an a. Right? Having noted that, now to the question of how do I compute a? Well, now x is playing a different role. I have to tie it down and say, okay, let's pick an x and stick with it. X is now a constant. And for the purposes of computing the area, this area of the cross-section, I have to treat x like a constant because it's better be a constant. It's for that constant value of x that I'm trying to understand the area. Does that make sense? Yeah. Cool. Okay. So the appeal that I make is that everything goes through the same. Again, the total volume of bread is the sum of the slices of bread. Each slice of bread is cross-sectional area times thickness. Who cares if it came out of a triangular pan? This cross-sectional area is still the area under a curve. It's the area under a curve as I move from there to there, namely as y ranges over certain values. And therefore that area itself is an integral dy. So we still, again, are going to have a dy integral sitting inside of a dx integral. It's almost exactly the same thing. There is really only, as far as we're concerned in this class, really only one difference. It's a subtle difference. But let's go back up to this picture. The range of values for y simply won't be constant anymore. In the rectangular case, given a value of x, whatever x was, the range of values of y, well, it was always c to d. Just c to d. But now, notice that for this value of x, we're starting at y equals 0. Oh, I should use, purple. We're starting at y equals 0. We are ending at, that value of y, whatever that is. Whereas, for this value of x over here, well, we're starting, as it happens, at the same value of y, but then we're ending when we get to the where the bread ends, right? That's the last bit of the bread there, and that corresponds to a different value of y. So, in this case, that upper bound, the upper bound for the y integral, is going to be different for different values of x. Anybody see that from the picture? Let me say that in slightly different language. The upper bounds for y, the upper bound for y is a function of x because it depends on x. Different x's, different upper bounds for the y range. All right. So so the way that comes out then in practice is here it is. That the y bound, here, looking for that cross-sectional area, the y bounds are functions of x instead of constants. Everything else is the same, which is fantastically convenient. Okay. All right. So how do we figure out what those bounds are? It's a matter of looking at the details here. I like to go through the following little process. It's sort of a 3-step process. The bound that I'm looking for, I'm going to loosely say it's determined by that point. I mean, where that point is what decides what that upper bound is. That point is where you get to the end of that slice of bread. That point is on a certain curve. In this case, it's that line. And by the way, let's not forget what we were given. We were given that this point over here is 1, 0. This was, this is 1, 0 there, and that is 0, 1 there. And so not too much trouble. You can show that this line that decides where that point is, that decides where that bound is, has equation x plus y equals 1. Right? And what that means is that this point x, y2, that point satisfies that equation, which tells me that x plus y2 is 1, And that tells me what y2 is. y2 is a function of x, and it is 1 minus x. All right, so there's a three-step process here. Recognize that your bound is identified by a certain point. Make sure you see clearly on your picture, where is that point? The bound is identified by a point. The point is going to be on a certain curve. Geometric object of some sort. That curve has a certain equation. Right? Again, we're connecting some dots. Bounds to points, points to curves, curves to equations. In that equation, just solve for what you're actually interested in. So again, in this case, we're interested in knowing y. So you solve for y. Everybody see the game? It's always the same game. Okay. All right, and that gives us our resulting integral. And this is just ever so slightly scarier than the previous iterated integrals we had seen. So let's see here. Our area, right, was this. Our area is what's inside our x integral. Our x integral is what tells us our total volume. There's that whole nesting of integrals that we've discussed before. What's different about this now is, it's still an integral inside of an integral. The integrand is still a function of two variables. I put in quotes, air quotes, because, it depends on where you are, which ones are variables. But worse, there is a function in the bounds. Now, one thing to set your mind at ease a little bit, this function in the bounds, this new source of worry, right? Can you do that? Are you allowed to have a function in the bounds? Let me point out that technically we don't have a function in the bounds. That's an illusion, right? It's kind of like, it's the same illusion that, previously we were thinking about x as being we have two variables in here, x and y, but no. For the purposes of the inside integral, y is the variable, whatever the inside differential is. That, in this case, y is the variable. X is to be treated as a constant. The variable of the outside differential is a constant for the purposes of the inside integral. So this x in here is to be treated like a constant, and again, that's important, right? Well, notice a nice upshot of x is a constant is that this bound that looks like a function, not really, it's just a constant. That x is a constant as far as the y integral is concerned. So it's just it's a slightly uglier constant to deal with as you go through the inside integral. And that's the only difference. Okay. All right, so let's see an example of this. So again, looking at this same domain, this triangle on the xy plane with vertices at those points, exact same domain. Notice that therefore I've got the exact same bounds. We've already gone through the process of finding the bounds in this case. Here we want to find the volume under a certain graph. Well, so volume sitting under a graph of that function. That function then is our integrand. And we have here now one of these new scary kinds of iterated integrals to compute, and it's no big deal. Let's just walk through it. We'll always go inside out, starting with the inside integral. Y is a variable. We're going to treat x as a constant, because it is, right? So our antiderivative, x being as it is a constant, that antiderivative is just x times y, because y was the variable. Notice we are plugging in so we had these bounds indicated, right? Y goes from 0 to 1 minus x. There's those bounds that I'm going to plug in. And notice, I just straight up plug in those bounds. The top bound, y is 1 minus x. That goes right where the y's are, thus turning that into that. And it feels a little weird to plug in a function in the place of a variable. You get the creeps doing that, right? But remember, you're plugging in a complicated looking constant. And for the purposes of this y integral, x is a constant, so 1 minus x is just an ugly constant. And so plugging in y, 1 minus x, is just a constant. How we doing? Okay. Conveniently, the lower bound, y equals 0, not only is a constant, but also looks like a constant. So no tricky curves there. And then everything else proceeds as it sort of normally would. So this resulting integrand that we get down here at the end, our inside integrand, that inside integral, is it's a function of x, just like it's supposed to be. Now, where does this function of x come from? What defines this function of x? Well, a couple of different things. The density function in here, or excuse me, the height. Generically, it's a density. So this height function, right? That and how this integrates is part of what defines this. But also the fact that we have these 1 minus x's here. Those 1 minus x's make their way into the algebra in the plugging in. Yeah, as they should. Thus resulting in a familiar Calc 1 integral plug and chug. All right, how we doing? Okay. All right, so here's the picture as it stands of non-rectangular domain, and how what does it look like to turn a double integral on a non-rectangular domain into an iterated integral. And there's an observation that I want to make, a couple of sequence of observations I want to make about this picture and how this broke down, that are, I think, really important, that are going to save you a lot of trouble, a lot of artistic challenge, which is a wonderful thing to save on, right? So, first observation. We just turned a double integral, right? We were interested in a volume, and therefore a double integral, which I guess I never wrote down, did I? Shame on me. Yeah, I never quite wrote that down. Well, I have it written down here. The double integral, its integrand was f of x comma y. And now look at the resulting iterated integral here. The resulting iterated integral, its integrand, f of x comma y. The integrand does not change. Now, that's just an observation. You look back at all the examples that we did previously for rectangles. Same deal. The process of turning a double integral into an iterated integral doesn't change the integrand. It's the same thing. Nothing happens to the integrand. That's the first observation. Second observation is, let me say that a little bit differently. The domain does not affect what the integrand is in the double integral or in the iterated integral. Second observation, likewise, the integrand does not affect the domain. So looking back at this picture, the way these bounds worked out, what's the range of values of x? X goes from there to there. Doesn't have squat to do with height. Right? The range of values of x is entirely dependent on the shape of the domain, and that's it. And how tall, whether the bread does or does not rise. Yeah, so what? The domain is what defines the range of values of x. Furthermore, the domain, and only the domain, affects the range of values for y. Right? The bounds are based on points. Those points are on curve. This whole thing happens in the domain. Right? Height doesn't affect it. So, the big observation to make is that all of this analysis in trying to figure out what the bounds are for our iterated integral, critically, that all takes place just in the domain. So you don't need to draw the whole volume picture. That was a waste of dimensions, right? We're dimensionally poor. We have 3 dimensions, grand total, to possibly be able to work with, and in fact we have 2-dimensional paper that we're working on most of the time. So we can't be, dimensionally wasteful. Here we drew a 3rd dimension that we did not need at all in retrospect, right? So the big observation here is be dimensionally frugal. You only need 2 dimensions. You just need to draw the domain to figure out what's going on with the bounds. So only draw the domain. Don't draw the height. So here's what that picture turns into. Here's that same triangle. So, our question was, we have this triangle. These 3 corners were given, and we want to, we're computing a certain thing. Well, we know we're computing volume under a graph. We've been through it a bunch of times. We know that volume under a graph is a double integral of height. So we know what our integrand is. Our integrand is the height. It's the f of x that's given. We don't need to draw a picture of that. Why would we bother? That's clear. We just need to figure out the range of values of the variables. Well, I can see here that as I slice, let's see here, as I make these, okay, my picture's gotten messy here. Let me, come on, eraser. Here we go. Let me erase all of this. As I slice the bread that way, notice that's what is actually happening on the domain. I am slicing up the domain in little straight line slices perpendicular to the x-axis. What that looks like over here is this. Right? I'm slicing up like so. And so one at a time, slices look like this. And those slices, x goes from there to there. And it's just a lot easier picture and easy appeal to make. Okay, well, my first slice is where x is equal to 0 and ... more slices. My last slice is a little sad little slice at the end. It's barely there. And that's where x is equal to 1. Look how much easier that picture is than that. Everybody see what I'm talking about? That's a nice streamlining of the process. Secondly, how do I go about finding the range of values for y? Once I fix a certain value of x, with x fixed, the range of values for y, well, there's the start of my y slices. Proceeds along until I get to there. That's the end of my y slices. And let's play the usual game. This bound that I'm looking for is determined by that point on the picture. That point is on that curve. That curve has that equation. Just like it was before, then I'm going to solve for what I'm actually interested in. The y bound, which is then 1 minus x. Same result. Same argument, really. Much better picture. Okay, so you only have to draw a picture of the domain. So now it's worth noting the relationship between what you're looking at here versus what you're looking at here. The only visual motivation the only connection that you have in your minds between converting a double integral into an iterated integral is this picture and the slicing up of this picture. So if it makes you more comfortable, and that's fine, if it makes you more comfortable to visualize this 3-dimensional picture as being, okay, this is what you're kind of doing when you're converting a double integral to an iterated integral, that's fine. But notice the slicing, this slicing of the solid effectively means you're doing this kind of slicing, that kind of slicing of the domain itself. So this is what all of our pictures are going to look like going forward. And let's see, it looks like we're out of time, and this is a pretty reasonable stopping point. Technically I guess we're done with, I'll do that example next time. That's fine. Okay, so yeah, see y'all later. I owe you exams. If you stick around for just a quick minute, I'll give your exams back.